So I think some people will be joining us as we move along, but right now we've got a good group. I think I got some fun experiments, some unique ones that you'll see. Okay, I'm going to pick up where I sort of left off on the last Zoom session that we had, and that was with an indicator. And I didn't mention an indicator before, something that I think is important about the indicator. Okay, oh, there's Deborah. Welcome. I've got my older lab coat on today because we're going to have some stuff that can really stain lab jackets. There's some silver nitrate I'll be using, and there's no way you get silver out of a lab jacket. Oh, we're getting more people joining us. And let's see, we have Marin now too. Okay, very good. So, like I said, we're going to pick up with acid base, in this case, indicators, and then we'll do something that I hadn't planned on doing, but I'll explain why I'll be doing that a little bit later. So, on with the show. We got some chemistry. As you can see, we've got a lot of chemicals out, and we'll see which ones we use. And if I don't use some today, I'll use them maybe next week. I hope you remember that we're using indicators to tell us if we had an acidic solution or a basic solution, even give a clue as to pH. And this is next to litmus. In fact, I think somebody mentioned litmus at the last video, which is litmus is a lichen. It's a moss that grows up north. And if you dissolve it in water and add acid, it turns pink. And change that acid to a basic solution, it turns blue. And litmus has been around, I think, since like 1100. It's been used by alchemists and such. It hasn't been used very much recently, though. It's, like I say, it's an ancient one. Now, the newer dyes, which were discovered in the 1860s, Victorian era, they're the preferred ones. So litmus is, it's not my favorite because it's hard to sort of see the pink. While here with bromethymol blue, one of my favorites, you can see the colors very nicely. Now, the key to understanding and the importance of indicators is in the acid-base equation. You know, you know a little bit about the dissociation of, or ionization actually, because this reacts with water to make H+, and I'm not going to write out bromethymol blue. It's a very complex molecule, and it has a number of pi bonds. And the number of pi bonds that it has one after another, alternating, will produce the color that you see here. In fact, it's a very interesting science, producing different colors because using pi bonds in carbon compounds. And I've identified yellow when it's got the proton on, and blue in terms of its conjugate base when the proton's been removed. And when you take the proton off, it sort of changes the number of double bonds. And like I say, it's a very, color science is interesting. And I wrote the equation, the acid equation for it. Ka is equal to the products, our colorless acid. This determines our pH. And the other product on top, and the, whoops, I forgot the second bracket to indicate molar concentration of the unreacted weak acid. Here's our acid, here's our conjugate base. Now, I've got this as green. And you say, wait a second, yellow, blue? Well, this is yellow and blue together. You know, the way we see things, it looks like it's a green to us when we've got an equal mixture of that. But I can change that. I'm going to use my pipettes, my pipette bulbs. The bulb has a spot where you squeeze it to get rid of the air, and then you've got a little button that says S to bring some of that acid up, and then it's got an empty on the side. These are still used in labs quite a bit. And oh, I've got a stir bar. Let's turn this thing on. Okay, no hands up yet. So I guess there aren't any questions quite now. I've got this stirring pretty nicely. I can see it pretty well there. Nice green. And not for long, because I'm going to put a bunch of acid in. Zam. This increased Le Chatelier will end up having the extra acid react with the BTB. That's going to disappear. This part's going to disappear. This is going to increase. So acid time. Let's add a couple of drops. It's being stirred. Just waving it on there is enough to change it. It takes a little while for this stuff to react. Remember we were doing the cranberry juice last week, and I experimented with the cranberry juice. You can move it back and forth to the same colors, but it takes a heck of a lot of acid. No, base. Here we go, a little bit more. I've got this acid is pretty dilute. There. Added about a half ml, I think. Shifted it completely. We now have a lot more of this. His concentration is greater because we added acid to it. Now, of course, I can go backwards. And, I've got to get let me draw up some base. I'll need quite a bit of this. This is sodium hydroxide. The other was hydrochloric acid. No questions? No? Okay, let me empty it. The base going, there, blue. Did I go too far? No, not too far. We could do a reaction rate as to how quickly this occurs. My guess is a first order reaction. I'm trying to get to the, overshot, not quite. I think I added a bit too much. No, it's coming back. In fact, I think that's a great green. There's an extra drop. Now it's green. Now, I've shifted it now so that we have equal amounts of yellow and blue. In other words, these two concentrations are the same. That's why we've got the green. Now, if there's more of the blue stuff, of course, or more of the conjugate base. Oops, wrong way. It's been shifted, and we got rid of the acid, and it's made all this blue. It's gotten back to green again. Some more. The base is pretty dilute. There, stay blue. I think it will. But when these two are equal, their concentrations are equal. The H plus is equal to the Ka, and the pKa is equal to the pH. Now, I know when that is green, our pH is 7, which means the constant for this acid is 1 times 10 to the negative 7. When you've got the in-between part here, when you reach the endpoint of the indicator, and these two are the same, the hydrogen ion concentration is equal to the Ka of the indicator, and the pKa is equal to the pH. In fact, when you want to get to a certain pH and you've got the right indicator, you say, okay, I want to get to a pH of 9. I'll use phenolphthalein because this pKa is equal to 10 to the negative 9. Okay, any questions? Indicators are fun. So let me get rid of this. No questions so far. All right. And I'll turn it off. And it's off. We'll get rid of the clear bar. And it's a bit blue, so I'd say that's a basic solution. Okay, I was going to go on to Redox, but one of the things I saw on Redox was if you looked at the textbook pictures of the electrochemical cells, you've got 2 jars. One where the cathode is and one where the anode is. And there was a glass salt bridge in between that had a solution in it. And I mean, those look ideal. And I was surprised. I regularly contribute to the AP teachers chat group. I provide some advice and whatever. And I was surprised that a teacher asked, where do you buy salt bridges? This is, you can see, here's our little salt bridge. And also, they asked about a piece of glass that was spent with rubber stopper. They wanted to buy this. I'll be back in a second. Give me a second. Okay, here I am. They specifically said, where can you buy these? I can't find these in my chemical supply house stuff. And I says, what? You know, I answered saying, you don't buy these, you make them. And I was surprised that here they were, a teacher teaching AP Chem, and they didn't know about bending glass tubing. So I thought I'd give all of you a chance to know how to bend glass tubing so that you won't have to ask that question. Typically, you get glass tubing in 6-foot lengths. I got this in 3-foot lengths. And this is what you start with. And, you know, I use the glass tubing all the time in a lab. You've seen, you know, labs, they've got curly Q glasses, bent glass. I mean, the standard icons that you see for chemistry involves bent glass. And, you know, big lab companies or universities have professional glass blowers to make their instruments. But for most of the time, you make your own bent glass. So, envelope, you get to see this one. Normally, you've got a Bunsen burner in many labs. I don't yet, and I'm going to use this instead. You can use a propane torch. Okay, it's my piezoelectric sparking device because we were getting gas, and it's time for me to get my matches. There we go. My little sparking device is working. Rats. But you can hear it, and I think you can barely see the blue flame that I'm getting there. By the way, I know where my fire extinguisher is. I'm going to lock this in place so it's not going to tip. And we'll take some of this glass. Now, the key to glass bending is to get a piece of glass that's the right size. I don't want to use a 3-foot piece. Instead, what you do is you make a little notch on the glass tubing. That's what I got this file for. Makes a weak spot. All you need is one little score. Put the score away from you, and it snaps. By the way, you should have a towel in your hand when you do that in case you do it wrong. Now, the ends of this stuff are very sharp. You know, it's broken glass. And one of the classic things that's done is you put the end of the glass in the flame, and you can see it's turning a little bit orange. That's the sodium in the glass. This is soda glass. You can't do this with Pyrex glass unless you have an oxygen torch. And then that softens the end of the glass, and it doesn't have that sharp edge. Here, I'm going to show you the polished and unpolished end. I'm going to switch cameras. Let me go to camera switch to the glass can be hot. This end is polished. It's soft at one end. This end has a sharp edge that'll cut you. So you fire polish both ends nicely. I'm going to get the camera back. Glass is very interesting. It doesn't have a definite melting point. It's a mixture. And as a result, that's a bit hot there. Let me get another piece. That is hot. I've got a piece of some business there. I'll put this again. One notch away from you, it snaps. And I'm going to put this in the flame, and you'll see the orange. That's sodium, which is in the sodium glass. And when it gets to that point, the glass becomes very, very soft. And then you can just bend it. Just like that. And here it is, bent very nicely. In fact, probably, let's see, I'm not sure you could see the sodium before. Oh, yes, I think you could have. And we've got a piece of bent glass just like this. Now, typically you have a wider flame, so you have a smoother bend, and you're set. There's another neat little trick you can do with the glass. Let me put this in here again and straighten it out. Let me heat it up. Okay, let me see if I can get this to a brushier flame, because this one's a bit hot. They are making the flame a little bit less hot. And there you can see the orange flame. Now I've got it soft enough so that it'll bend on its own. And here's the other trick. When you get it really soft, you can take it out of the flame and stretch it out. And I'll turn the flame off right now. The glass is so thin that it's flexible. Here you can see it wiggling back and forth. And there I bent it all the way across. And I'm not sure, let me put this down so this isn't in the way. A Bunsen burner propane tank, use a soft flame and get something for your hands, because you're going to touch some of the hot glass and you're going to burn your fingers. I'm going to do another demonstration next week where it's a little tricky. And oh, by the way, if you snap this should be cooled by now because it's thin. The thin stuff cools faster. This tube, this glass tube, is hollow all the way through. You can use it as a mini dropper. Let me switch over and show you. You can actually, camera. Where? Let's see, can you see? I'm going to bring this out here. Barely. You can see it flipping back and forth. In fact, this is how you can make fiberglass. It's hollow all the way through. You can get many drops with that. And that was sort of a standard thing in biology. If you wanted to make your own dropper out of glass, you take some glass tubing, stretch it out, and often if you're in a lab with a lot of people having fun, you'd have a contest to see who can get the longest capillary, whether you can make it 6 feet or 10 feet long. We'll do a little bit more with the glass next week, but now if anybody needs some glass tubing, you know how to bend it, and then there's some tricks to getting it inside the stopper, but that's it. You don't buy bent glass tubing. Or maybe you do. Maybe we can sell it to people who don't know how to do that little trick. And again, if you're going to try doing this on your own, make sure you get what's called flint glass or soda glass, which has a lower melting temperature or softening temperature than Pyrex or borosilicate. You need an oxygen torch for that. Oxygen propane torch. Okay, let's now go to oxidation reduction. Now that you know that basic skill, you'll be very popular in labs. Okay, oxidation reduction. Let me do a little bit of erasing, and then we can get started there. Yep. Glasses and my little spray. Here you see to the right, I've got a reduction chart. When I first started teaching, they were oxidation charts. where it was exactly the opposite. But then around 5 years after I started teaching, they switched over to reduction charts. I'm not sure why, but I had to accept it. And if you go to an old university or a college and they have some tables up, you might see an oxidation chart, which is the reverse of this stuff. Okay, let me get out of the way so you can see the reduction chart. I'm checking for any hands. Oh, one hand. Yes, I see a hand. Yes, what was that question? Please. What was that? I'm seeing Annalise, you had a question. Annalise, you can put your speaker on. Where are you?
I actually didn't realize I had my hand up, but I didn't have a question yet.
Oh, you can make one up. No, no, that's okay. I won't put any pressure on. Okay, at least I saw the hand. That's good that I'm watching that. So maybe I'll get a chance for a question pretty soon because the Redox stuff can. Oh, let me ask a question that you can answer. Reduction chart. I've got part of this. In fact, it used to be on the AP exam. In addition to having equations and a periodic table, by the way, on multiple choice section, you can't tear that periodic table out. On the FRQs, they give you a separate book. They used to have a reduction table as part of the exam. So if you had a question on oxidation reduction, you'd have to flip over to look at the standard reduction table. Now they give you the data as part of the problem. But it's a great reduction table, and this is where I get my data from. And as you can see, here we've got a bunch of substances. Now, notice most of them have charges and are metals. Now, here's magnesium with a +2 charge, a zinc with a +2. Well, this isn't a metal, it's hydrogen. It's our acid. Copper, here's an exception, iodine. And this will be interesting at the end. This is one of the last experiments. Silver with a plus and gold with a +3. And these are materials that reduce. And it sort of makes sense because they have a positive charge. You'd think that they'd attract electrons. In this case, gold with a +3, grabbing 3 electrons, become gold metal. Quite different, of course. I mean, gold metal, here's my gold bar. Remember, I got this deal of gold bar. I got it on the internet, and I got it for $3. Actually, I paid $9 because I got 3 gold bars. So here's my $2,000 gold bar that I bought for $3. And of course, this is what it's like when it's got its electrons. Without its electrons, as +3, it's an ion. And you can buy gold chloride, well, actually, you make it yourself, where it's in solution. Like here, I don't have any gold solution with me right now. One of these little strips is silver, and we're going to have to figure out which one it is. And of course, it looks like silver, like the silver you have in rings and stuff. And so that would be this stuff, silver with its electrons. And if you remember back, I think it might have been in October, I had AgNO3. Here it is in this container. I'm going to pour some out. Pretty dense stuff. It looks just like salt. No way you would mistake this for silver because it is silver ion nitrate. Because you can't have the ions by themselves. You have to have something with it. And I hope you all remember, because let's see, you're not going to pass the AP exam unless you do, that all nitrates are soluble. All alkali metals, sodium and potassium, ammonium, and nitrates all dissolve. So let's give it a chance to do its thing. Here I have some distilled water in my water wash bottle. It's pure water. I can't use tap water because tap water has some chlorides in them, and those chlorides would react with the silver to make silver chloride. In fact, there's a that question that you asked, Annalise, about silver, the question about the silver chloride, we'll do a video on that. I also do a demonstration on that later. Okay. Clear solution, but there's silver in there. It's silver ions. Silver sans electrons. No electrons. It's an ion. You could even mistake this for distilled water. It's not exactly toxic, but I wouldn't drink it. Some people do. It's strange. Computer. What's the reduction potential of silver ions?
The reduction potential of silver ions is plus 0.8 volts compared to the standard hydrogen electrode.
Voltage is a measure of the push or pull of electrons. It's measured in joules per coulomb. It's always per 1 coulomb. If you have a coulomb of electrons, what is the push in joules, force? The energy needed to move things. And as you heard, computer was right, 0.80 volts, but it said compared to the standard hydrogen ion, which is here. Compared to hydrogen ions, it is 0.80 better at pulling electrons. What is the reduction potential, the standard reduction potential for hydrogen ions? In other words, here we got some hydrogen ions and they're grabbing at electrons. That's what reduction is, the pull on electrons. What is the standard pull from hydrogen ions? Yes, answers all over the place. I'm seeing them everywhere. I think everybody's answered. Let's see. Oh, but I think Maren was first. Okay, Maren.
Is it 0?
0. Exactly. Oh, I'm going to keep asking a question. Does that mean it doesn't have any pull or attraction towards electrons, Maren? Putting on.
No, it still does.
It still does, but why is it 0?
I don't know.
Yeah. Well, that's worth getting the answer for. Deborah, you were going to answer that.
It's a reference point, so it's not saying it's 0. It's saying we need like a middle ground standard. So relative to the other stuff, it's less or more.
Boy, that's better than I could have said it. Yeah, I like that. It's sort of like the middle that we compare everything to. It's the standard. It does attract electrons. Oh, let me get the right one. I'll use this one here. And you're expected to know that. I mean, they expect, they have some questions where they don't tell you what the voltage for the hydrogen standard electrode is, because they know you should know that it's 0. Silver, in terms of volts, joules per coulomb, is 0.8 compared to hydrogen ions. And so silver is much better. I mean, here, I've got some 1 molar hydrochloric acid here. We'll be using this in a second. I put my finger in here, and it's going to try grabbing some electrons from me. And it's going to be pretty good at that. It's going to spark. It would. I've done that by accident. Put my finger in here. It's going to take electrons from my finger and turn it into silver, and my finger will have powdered silver on it, and the silver will have gotten my electrons. So I will have given my electrons to silver. In fact, typically, if you're working with silver nitrate, you're going to end up giving spots on your hand and your lab jacket. That's why I've got this lab jacket on, because I'm going to get a few drops of this stuff on. It happens. It's inevitable. It's as if it knows that it wants to get that electron. And there'll be little brown spots on my lab jacket where the silver ions grabbed the electrons from my jacket and turned into metallic silver. And fine powdered silver, like any powdered metal, except for aluminum, is black. or a dark, dark, dark brown. That's how they used to have film. In fact, that's how they made film. So these guys are ready to grab electrons better than H plus by 0.8 of a volt. But the lousy stuff here is the zinc and the magnesium ions. They're really, really lousy at grabbing electrons in terms of comparison. So let's have some electrons being grabbed here and there. Let me start off with a little bit of this silver. Nitrate. +1 charge. I won't need much of it. It's expensive stuff, so I won't use a lot of it. And I'm going to take and I'll add some more water so we can see it. I knew silver is better at grabbing electrons. Now, these things on the right have electrons. My copper here at 0.34 will grab electrons, become copper metal. But silver is better at grabbing electrons than copper is holding on to its electrons. So this silver ion will take the electrons from this copper and change it to copper +2. So copper wire in there, and I'll add some more water. I'll add more water. We can see it better. And guess what? I'll add a little bit more silver ion in here so we can see it better. A little bit of silver nitrate. By the way, they use Luna caustic. Oh, that's its old name. The old name is Luna caustic. And the reason it's called Luna caustic is because as a solid, and you put it on some skin, it will cauterize, quotation marks, burn the skin to basically sanitize it. You'll find that doctors will have little pencil sticks, and at the end of those sticks, they'll have some silver nitrate. And if you've got a wound or a bleeding spot, they'll touch it to that wound, and that will sanitize it, kill the bacteria, but also create a little bit of burning, and that will supposedly stop the bleeding, cauterizing, rather than that's one way of solving a small capillary bleed. You use a laser or you use some silver nitrate. Now this is starting, the copper wire is starting to turn black, powdered silver on. Okay, looking for questions. Okay, I don't see any questions yet. Oh, there's a question. Yes, Philip. You'll have to turn your speaker on.
Yes. I just wanted to know the Luna part from the Luna caustic, does that come from the fact that silver was associated with the moon?
Yes.
Something?
Yeah. In fact, your alchemists, they didn't have our symbols that we have now. In fact, our symbols are still pretty strange. Like, why is silver called Ag? Well, the Latin argentum. And the alchemists, if you look at any of the books, they have images of gods and goddesses, and they would associate the different elements that they had found, and they found quite a few, with different gods. And they didn't want to tell anybody exactly what was happening. You wanted to keep things secret. So they used those strange names. And those names have hung around. The Luna caustic, there's liver of sulfur, there's all sorts of strange names that alchemists have used. And sometimes, even today, certain groups will use those names besides being artists. Okay, our silver is growing. Yep, another question somewhere. Maren.
Well, it wasn't exactly a question, but I do remember hearing a little while ago when I was kind of studying a little thing about silver. It's also called Argentinium because silver was very prominent in Argentina, is what I heard.
No, actually, it's the reverse of that.
Oh.
The argentum, the Latin term, was around, during Roman times, certainly, Julius Caesar, when the Spanish came to Argentina, or at that area, Tierra del Fuego, they found silver, and they named it the land of silver. In fact, it was sort of sad because the original inhabitants of Tierra del Fuego were enlisted as slaves to do the silver mining. And when the silver that they had was in real fine particles in the rock. So you got enlisted, first of all, to smash the rock to get the little pieces of silver, but they were too small to pick out. Spain had a lot of mercury. So their ships came to Tierra del Fuego and brought the mercury. Mercury will dissolve silver. I mean, if you have a silver ring and you drop it into a pool of mercury, the silver will dissolve. It'll melt into it. So they would pour mercury over these rocks. The mercury would dissolve the silver, and then they'd pour the mercury into vats and boil it. And the mercury fumes would leave, and you'd have silver ingots left behind. But of course, if you're around where the mercury was being boiled, you were poisoned by the mercury fumes. So if you, firstly, I think they kill like 95% of the population because of that, the natives who lived there. So the land of Argentina, a sad story. Okay, let's get to oxidation reduction though, because, you know, we got oxidation reduction occurring here. Let me get some other oxidation reduction occurring. Little beaker, copper. Copper is pretty good at grabbing electrons. It's higher than acid is, H+. And I'm going to dump in not something that I hope will, let's see, copper ions. They could take hydrogen. I'm not going to use that. They could take zinc. They could take magnesium. Okay, I got some magnesium here. Now, open it up. Put some magnesium in. And we're going to make some copper metal from copper ions. Oh, it's fizzing already. Oh yeah, there's a big difference in reduction potential. We have an oxidation reduction reaction going. We're going to make stronger bonds. It's exothermic. And if I had powder there and put it in, the reaction would happen so quickly that we'd start to have some boiling take place. So here's an oxidation reduction. Copper ions, grabbing electrons from magnesium, making magnesium ions. So we're going to be making brand new copper metal, just like we were making brand new silver metal here. But volts, that's what we're up to. So let's get some volts going. I've got my H+, that's good at grabbing electrons. And I'm going to get another cup. Here's my silver. I got to move that to the left. And I'm going to put in, where is it? Here it is. Some ionic compound. Actually, it's sodium chloride, and we're going to ignore the sodium. My H+ is here, ready to grab electrons. Right in the speaker. Like I say, you put my hand in there, you'll take electrons from me. And I'm going to get that magnesium. I'm going to put it right in there. Now I'm going to get a graphite pencil and put it in the acid. Amazing. You get these things like for $10, these voltmeters. I don't know how they do it. I'm going to connect these two. The difference should be 2.37 volts. Magnesium, you got those electrons, but not for long, because these hydrogen ions are going to take them. So rather than my finger taking them, this pencil has graphite in it. It's a conductor. The graphite's inert. I could have platinum there, but if I had platinum electrodes, I wouldn't be teaching. Put these two together, and we'll turn my voltmeter on. Whoops. Come on. Hold. My magnesium is being stubborn. There, I'll bend it so that It doesn't have any choice. There. Lose your electrons, magnesium. Turn voltmeter on, and I get 0. Nothing. The H plus can grab the electrons. The magnesium has got the electrons to be grabbed from, and it can be. Why am I getting 0? Annalise.
Because you need a salt bridge to balance the ionic charges.
Yeah. Right now, if the electrons move, we have an imbalance of charges. We got magnesium ions, Mg+2, but no ions to match for it, anions to match for it. The cations are there. They need some anions, hence our salt bridge. I got a fancy one here. I'm going to check to see what happens to my voltage. I'm not sure if you can see it. Zap. Wow, 2.08 volts. Instantly. Because we could have that flow of current. Now, these things are pretty fancy. They're a pain in the neck to make and fill. I got little cotton things at the end of them. Most people don't bother with them. They're just there for show. They look great in illustrations. Instead, I'm going to make a salt bridge using some paper towel. Wrapping up some paper towel, giving it some ions. This is salt water here. Put this in between. Voltage, just as good as before, 2.09 volts. Now, theoretically, oh, wait a second, 2.10. That's pretty close to the ideal. It's not ideal because I don't have 1 molar solutions and I don't have the world's best. Well, I bet this is a pretty good salt bridge, 2.1 volts. We got the magnesium ions losing their electrons, going through here and going to the H plus, making a hydrogen gas. Remember the title of the, let's see, I'm looking for hands, of the Zoom session? I said I was going to do buffers. I didn't do buffers. I tried doing it. My pH meter was lousy. Yes, Philip. You were going to answer the question?
Mr. Moskaluk becomes a redox conductor?
Right. Zero right now. .96. Let me wipe my hand off from the acid. Indeed, I was a conductor. Not quite as good as the paper towel, though. The paper towel is a better conductor than I am. And really, if you put your hand in both of these, let's put this up so you can see it. I think you can see the voltage, yeah. In fact, this way will go across me completely. Yep, 2 volts. I'm a conductor. Let me rinse my hands off a little bit with the water. Where's my waste container? Here's my waste container. So it doesn't take much to end up getting to be a conductor. Just put anything between those two and you will get yourself a conduction of electricity. Okay, any questions so far? No. Well, I fulfilled the lesson there. Yes, there was a question. Philip.
What does it feel like to be a conductor? Like, does it feel
Nothing.
funny?
No. I was surprised that I've done this a number of times with some other solutions, non-acid solutions, where I try to, and I don't feel any tingling or any electrical movement. Now, the first experiments done with conducting electricity in two different metals were done by Luigi Galvani, Galvanic Cells. And he did it by he found out by accident, taking a copper probe and an iron probe, and he had some freshly killed frogs. And he would touch the frog muscles with the copper and the iron, and the frog muscles would twitch. The frog muscles were part of the electric circuit, and the electric current on the freshly killed frog legs would cause it to move. And that's when they discovered electricity was involved in all of our muscle moves. Our neurons make electricity to make our muscles twitch. But you could also make them twitch using this. Now, I guess if I would have exposed some muscle tissue and used those two probes, I could get a muscle to twitch. But for some reason, when you're a salt bridge, that doesn't, at least I don't notice anything. Galvani thought that the animals themselves were making the electric current. Volta said, no, it's the metals. And Volta was right, and hence Volta, we've got our volts. Yes, any other questions? You had a further question, Philip?
Yeah, I don't understand exactly how the ions can flow through you, because
I'm an electrolyte. In fact, actually, what happens is some of the electrons go into my skin, then other ones go out. And
but don't you need to have ions going through your skin, basically? And then once they're in your blood, that's
well, my blood's got sodium chloride in it, magnesium chloride. You are a great conductor because you're a solution. I've forgotten what the molarity is in terms of salt, but
it has to, like, the ions have to just jump through that little bit of skin first, right?
yeah,
how do they do that?
I guess the skin's permeable enough for that. There's probably enough moisture there. In fact,
well, that's cool anyway. It's really funny. I wouldn't have thought that the ions could just go like right through your skin, but I guess that's kind of why you get like wrinkles when you go in a bath.
Could be. Yeah, you probably would be better at that. Here. Oh, darn. Oh, this is going by too fast. We're at 0 right now, right? Even these nitrile gloves, I'm getting 0.04 of a volt, 0.06 of a volt, 0.07 of a volt. That is surprising. I would never have guessed that. Okay. Now, here we go. I have to solve too little time. Here. I can get rid of the magnesium. And I'm going to put in some copper. Oh, and I need to get my salt bridge. Here, I won't use me. I'll use this. I'm getting about 0.45 volts. But now the electric current is going in the other direction. And we're having the copper ions, because there's copper ions there that are, in effect, pushing the hydrogen back because there's some hydrogen present there. Now, my voltage is 0.42. Now, explaining why, in fact, actually, let me, because of the time. You got a voltmeter as part of your lab kit. You should have a voltmeter home somewhere. Get yourself a nail or some zinc and some copper, a penny, You can use the nickel that's in a quarter or a coin. The cells in the salt bridge act as the cells in the lemon act as a salt bridge. I'm getting about a half volt with this iron and copper. I'm switching over to silver. Silver is higher up. I theoretically should have a higher voltage. I did 0.58 volts. Why? Because silver is better at taking the nail electrons from the iron in the nail. Silver's up here. It's better at taking the electrons from, iron's down here. I should have had iron in there. In fact, actually, let me switch to zinc. No, we'll use iron as our guide. Now, here's gold. This should be even better. What? 0.27? Gold's better at reducing than silver and getting a lower voltage. What's wrong? Annalise.
It's not actually gold. It's a different
Oh.
metal.
Darn, why? I mean, how is that possible? I paid $3 for this. Yeah, it's not gold. They told me it was. But I guess if I was getting it for $3, there was my test. You could use this as a test to find out if something has the right reduction potential by these comparisons. Speaking of our oxidation reduction, let me quickly switch over to my camera here. Silver that was in solution now are these silver crystals. That silver ion gained its electrons, taking it from the copper, and notice the solution is turning blue because copper ions are being made. That copper wire is now copper +2. Here, my copper ions are changing into copper metal. I put some, I think it was zinc in there, and it reacted. So here we've got the oxidation reduction done without a cell. It happened all by itself. But here, in our other cases here, we were able to channel the electrons. I mean, on these two, the electrons went directly. But it's so nice when you can channel the electrons through some wires, because then you can run motors. I mean, all of our electric cars are run by a chemical reaction between some lithium and, I forgot, the lithium hydride was the other part, where you've got an oxidation reduction reaction, but instead of happening all by itself, you make the electrons go through a wire and use their energy. Whoops, hang on. Oh, I got to change back. We could make those electrons go through a wire here rather than reacting directly. And when that happens, we can channel the energy. Instead of getting heat, we end up getting an electrical energy that is very, very useful. I mean, your watches, everything that's electrically powered with a bunch of batteries. This thing, I'll use this on the next case. It's a chemical reaction and oxidation reduction. But instead of happening all by itself, we force the electrons to go through a wire. And when those electrons go through a wire, they produce a magnetic field. That magnetic field can do all sorts of neat things. The salt bridge, though, is really, really critical. as much energy as goes through the wires has to go through the salt bridge. If that salt bridge is destroyed, the reaction occurs all by itself. There's a Nobel Prize won for being able to make a salt bridge that could handle huge amounts of electricity. If they don't, your salt bridge breaks, the electric car's battery will burst into flames because you get the oxidation reduction reaction occurring all on its own without having to go through the wire. So, every time you see a battery like this, or a car battery, realize that you've got an oxidation reduction reaction ready to take place. A lot of energy be released, enough energy to drive a car 300 miles is separated by a salt bridge. Without that salt bridge, the reaction goes all on its own. And you get an exothermic reaction. Okay, next time, I'm going to force some reactions using my battery. And that'll be next week. I think it'll be about the same time because rats, we've got 1 minute left for questions. Yes, Maren.
So I just had a question about when it comes to calculating voltage. I know in your outlines, it was saying that the E of the cell was the voltage of the reduction minus the oxidation. But then I was also looking in the AP textbook and it said that it's actually the oxidation plus the reduction. And then the voltage switches depending on whichever half reaction is reversed. So I just wasn't sure which is the right way to do it.
They're both the right way. And I've taught both, and I've had my best success with the subtraction method. And the reason for it is when this goes, it's plus 0.8. When this goes, it's going backwards, so it's negative 0.53. And then you'd add the two.
Gotcha.
One method of teaching it is to find out what's the reduction, what's the oxidation, change the sign of the oxidation, and then add the two. The other method is one I've had the most success with. If you understand that, you know why I use the other one, because it's simpler. You take the reduction reaction and you subtract from it the reduction voltage of the oxidation. The minus sign does the changing automatically. And that happens.
Gotcha, thank you.
Yeah, I think maybe it's being mean of me to say, if you don't have to think about it using the subtraction one. And if you're smart enough to know why does that work, then the subtraction one makes sense for you. So that's what I've been doing. Yes. So I'm glad you asked that question because really it's something that you should have thought about. Yes, Phil.
I was wondering, so I saw in the summary that you made that platinum has a reduction potential of 1.19 volts.
Mm-hmm.
And I thought you said that it had the greatest reduction potential of any metal, but it looks like gold has 1.82.
I'm gonna have to look those two up. There's when you get to extremes, there's a couple of other reactions that are involved, and I'll have to look that one up to find out. Platinum is got to be really close to that of gold. It could be no. Again, I'll have to look that up.
Okay.
Okay.
I was just curious. I was really curious. So I looked up like all these different platinum compounds that you can actually buy, like platinum salts.
Wow.
Which is cool. Like some of them are used in chemotherapy. Yeah.
In fact, I was lucky enough to go to the lecture of the guy who made the discovery for that chemotherapy. It was an amazing discovery, and it was an accidental discovery. And if you get a chance to read about it, they were expecting something else, and they were using platinum electrodes, which was pretty standard in a lot of chem labs. In fact, when I first started teaching, platinum was a lot cheaper, and you could buy platinum electrodes. And they thought the chemicals in their reaction were causing the cell growth to differ in these bacteria. And they found out that the platinum electrode was being oxidized to make that compound. And once they found that compound by accident, they used it as the platformate for the cancer treatments. In fact, he's the guy responsible who gave that lecture was had a element named after him. He was the only living person to have an element named after him. And Glenn Seaborg, I've got his autographed book on how to teach chemistry. Okay, we're beyond that. So
That's cool.
yes, yeah, it's one of my favorite things. I've got it in the library. I'm answering your questions on the discussion board. It's right up there. Glenn Seaborg and his autographed copy. Okay, now, so I think that's about it. We're a little bit beyond time right now. Next week, I'll force some reduction using a battery, and maybe I'll show you another trick in glass blowing. And like I say, I'll see if it works. I'm gonna be experimenting with it. It's a really special trick that they did 100 years ago that isn't done anymore for a good reason. Okay, everybody, I'm glad we had a good group together. I'll post this video probably by tomorrow in case you want to see sections of it, and me being a conductor, of course. So goodbye. Get into that review. There's a lot of great questions there. And if you have any questions on that review, please go under the discussion board and I'll help you with them. I look there every day. Okay, thanks for coming and really appreciate an audience. Okay, goodbye, everybody.
Thank you so much.
Thank you so much.
Thank you very much.
Oh, you are all welcome. It's good to hear your voices. Love it. Okay.